In this lecture, we will be learning about the ARIMA-GARCH process. Let's review a bit. First, let's recall the definition of an ARMA-PQ process. So we'll have a white noise, and notice for an ARMA process, our white noise has a variance of sigma sub epsilon squared. And we say our process Y is ARMA, or autoregressive moving average of order PQ, if for constant parameters mu, then we have thetas and phis, we have the following expression. And so this is a model where the way yt differs from its mean has memory of how it differed from its mean in the previous time period, all the way back to p periods ago, a new noise term, and then some memory of the noise terms 1, 2, up to q periods ago. And this is a very common model used for stationary time series. You have a lot of different autocorrelation, autocovariant structures that can be used depending on P and Q. And yes, a very robust model for stationary time series. Note that many time series in reality are not stationary, and so we take their derivative or difference them and move to ARIMA models. And we review this definition as well. And we say a time series xt is said to be an autoregressive integrated moving average process. So this is the additional wording, integrated, if we difference it d times and we recover an ARMA PQ process. In such a case, xt is ARIMA PDQ, where d is the number of times that we difference it. And the way you want to think of this is that d is the minimal number of times we have to difference the time series xt in order to achieve stationarity. So we differentiate xt d times to achieve stationarity, and that gives us a new time series, which we'll call yt. And yt is then modeled as an ARMA PQ. And recall, just quickly, the differenced time series. So our time series delta xt is nothing more than the time series formed by the differences of adjacent entries in the original time series xt. So in this context, we take xt, we differentiate d times, we then believe the resulting process, which we call yt, is stationary, and model it as an ARMA PQ. Again, there are conditions to have stationarity for your ARMA, but those are exogenous to this lecture. Then we can integrate yt d times to recover our model for the original xt. Now, one key thing to note here is in these models, we have this white noise process. And this white noise process is something that results in what we call homoscedasticity and conditional homoscedasticity. And we're looking for heteroscedasticity. So we're looking for a process such that when we take the conditional variance of the process, we get something that changes in time. This type of white noise process does not provide that. So our goal is to replace our noise term with something more sophisticated. And we review our definition of our GARCH PQ process, which is the new noise term that we're going to use. And so recall the definition of a GARCH PQ. We have a white noise process, but it's different now in that it has variance 1. And we say AT, this is our candidate for the new noise process. AT is a GARCH, or generalized autoregressive conditional heteroscedasticity PQ, or GARCH PQ process, if we can write AT as the product of sigma t, defined below, times this, you could say, standard white noise process. So everything variance, whether unconditional or conditional, is handled by this sigma t. And we have parameters, some alpha parameters and beta parameters. And the idea of sigma t, which is the conditional standard deviation of AT, given past values of A and sigma, is that the conditional standard deviation of our process AT has some memory where it remembers Q past terms of the noise process itself and P past terms of the conditional standard deviation itself. And again, we will review some of the properties of this. If you take that defining equation and substitute this sigma in equation 3 into equation 2 and square both sides, this is what we get. And recall that this AT square looks a lot like an ARMA model for the square of AT. So you have memory of two past things, both the noise process itself and the conditional standard deviation. The difference between an ARMA model and this, the main thing is the noise is multiplicative rather than additive. And the idea is that you can get regimes of high or low conditional volatility. This is a good process, AT, for a noise because it's weakly stationary. It has mean zero. It also has conditional mean zero. It has a constant variance. That results in it being weakly stationary. It has no autocorrelation. So these are key properties that we want for a noise process. But the process of AT squared has autocorrelation, and it's the same autocorrelation of an ARMA PQ. And it's that autocorrelation in the AT squared that shows there is dependency, there's autodependency amongst the AT, amongst the noise terms, but they are uncorrelated. There's no autocorrelation. So this gives us a nice term, a candidate for a noise term, that has this property of conditional heteroscedasticity. And remember, that means the conditional variance or the conditional standard deviation, as written in equation 5, changes in time. And we can see it changes in time simply because we see the feedback of these prior values. So now comes the moment where we now actually use this GARCH process AT as a noise term. And we combine this with the idea of the ARIMA model. And so putting this all together, we define our GARCH ARIMA model in the following way. We let epsilon t be this standard white noise. So white noise mean zero, variance 1. And we say a time series xt is said to be GARCH PGQG, ARIMA PADQA, if we define a new time series yt by differencing d times xt, and that yt is an ARMA PAQA process with a GARCH PGQG noise term AT instead of the standard epsilon t that we saw in our definition of an ARMA model. So this sounds like a lot, but we're really bringing together these different types of time series, namely the ARMA or the ARIMA and the GARCH time series. And remember that it all boils down to the following idea that this definition here, this equation 8, is the defining equation for an ARMA process. The only difference is you have these A's instead of epsilons. And that's really all this is. We have our ARMA process with just different noise terms. So we start with our time series xt. We difference it d times. We believe that that d times differenced xt, which we call yt, is stationary, and we thus model it as an ARMA process. written here, but we use these fancy noise terms as defined in equation 6. So we have the noise term AT defined in this way as our GARCH process. We see we have QG past noise terms showing up with feedback, and PG past conditional variance terms showing up with feedback in the current time t conditional standard deviation. So all the work that we've done to develop this GARCH process is giving us the ability to use it as a new noise term. So the way that we look at this, if you're given that data, y1 to yn, so this would be the result of differencing the original time series d times. When you actually fit your models, which we will look at separately, you will get residuals, just like you would if you did, say, an ordinary least squares fit of an autoregressive order P process. You get residuals, and those residuals are the actual data values minus the predicted values. So think of this when you have a regression and you have your predictors down here, and up here you have your response, and you have your data points. You do your regression line here, say this is the teeth case. So here would be the data point. This would be the data point yt. And then here on the line would be the fitted value, the value predicted by the regression. And the difference between the two is the residual. Our residual, written this way, would actually be the negative of what I'd drawn, but we're typically looking at the squares of the residuals, right? We do these typically by some type of least squares type fit. The residual is that difference between these two, which we can also interpret as the data point minus the conditional expectation of yt given all your predictor information. So our residual for the teeth residual is an estimator of the teeth noise term. So this AT, right, this is our GARCH PG QG from that process. So each residual will be an estimator of the theoretical GARCH process, which represents our noise. And we can then use these for forecasting as we do with ARIMA forecasting. So if you watched a lecture on forecasting using ARIMA models, all of those techniques apply in this case where you replace epsilons with A's for your noise terms. We also can look at the standardized residual. So if you take your AT and your estimate for AT, your residual, and you divide it by the estimate for the conditional variance at time t, you now are estimating that driving white noise process that has mean zero variance 1. And this becomes incredibly useful to check fitting, or as people often say, goodness of fit for your model. So if your model fits well, first of all, these epsilon t's should not exhibit autocorrelation. So neither epsilon t nor its square should exhibit autocorrelation. If you see autocorrelation in the time series for the residuals or the square of the residuals, that's evidence of a poor fit of your model. Further, if you assume that your epsilon t's are from a specific distribution, say the normal with mean zero variance 1, you can then test your residuals for normality. And this isn't just true for the normal, this is true for whatever distribution you may assume your epsilon t's, or we call these innovations, are coming from. So we can see that we have the ability to work with goodness of fit issues when we have a fit of a GARCH ARIMA process to data. And really the key thing to remember from this is this allows us to build in this concept of conditional heteroscedasticity to our ARIMA models. And if we think about this from applications, this is very commonly used in financial modeling because it is often the case that we see evidence of even heteroscedasticity, which is tough to model. So we model it typically with these types of processes because it's a way to model the conditional heteroscedasticity, and that's typically enough. And you see that again in things like asset returns, where you see periods of market calm and periods of market higher volatility, where things maybe are not going so well in the economy. And a model like this is a good way to model time series in finance and allow for that, the different regimes of conditional variance.